Okay, object-oriented Bayesian networks, so this is another common extension. This is available in a GeniRisk, explicitly supported. Now this monster was my honours thesis BN, so I was working with the Water Studies Department at Monash University to model the native fish populations in the Goulburn Valley, and we created a BN which was quite a mess, really. So on the surface, it's quite difficult to sort of work out what's actually going on there, or when we first created it. And we did a whole load of things to try to make it readable, which you're seeing the more readable version here. So this is actually out. So we did some colouring of nodes here to identify, basically these yellow nodes are summary nodes. So there's a whole lot of, so for example, up in this section here, we've got a whole lot of nodes relating to the hydraulic habitat of the river system there. So whether there's a dam there and how that's going to affect the flow within the different seasons. And then we've got these summary type nodes here. So how good is the river flow in the hydraulic habitat in that particular area there? What's going to happen with the floodplain inundation? Is there going to be a decent amount of floodplain inundation? We've got other things on structural habitat like riparian vegetation and snags and whatnot. Water quality, so pH levels, turbidity, salinity, biological interactions, et cetera, et cetera. So we had this big mess of BN, so we've done a few different things here, like colouring nodes to make them kind of obvious what the purposes of it are, and we can put a key on the side there to talk about that. And we also put these big boxes around things to identify that these nodes are all kind of lumped together. They're all part of a similar sort of theme going on there. Now when I created this is when Netica was pretty much the only tool out there. Well, I wasn't really aware of any of the other tools there. But Genie and Huygen came about and actually they identified that these things were a problem, and then they kind of had solutions for it. So what we do, so we have some sort of issues here. We want to be able to sort of build and validate our sub-models individually. There's like an expression of the thing so it's actually understandable, but also the experts that I'm going to ask about hydraulic habitat are going to be different from the experts I might be asking about biological interaction. So I'd like to actually deal with this part of the model independently of that part of the model there. We want to be able to view it at different levels of abstraction. If I show this big mess of nodes to our stakeholders, they're just going to lose interest if they can't really understand what's going on. One of the biggest advantages of Bayesian networks is that we can be explicit about what's actually going on with Bayesian network. We don't want to lose that. We want to reuse subcomponents as well, like that hydraulic habitat might be applicable to other sort of species within the river system, but the modelling that hydraulic habitat is going to be the same. And we also might want to have multiple copies of the same sub-model within a BN. Now, Genie is good for doing, well, it's pretty good for most of these three parts here to varying degrees. Certainly good for building, validating, and the viewing. A little bit good, okay, for reusing subcomponents. Not good at all for this, not very well supported for this, combining multiple copies. Now in our Genie model, and I'm going to go across it back over to my machine for demonstration. So in the folder that we gave you in the example BNs, this one is in the Goulburn, where is it? Genie BNs? Goulburn fish structure here. There's nothing really much in this, it's just the structure. Copying the numbers across between the two different BNs didn't seem to work very well. Stevens developed a tool which will port models between these different, from Netica to Genie, and you do actually retain the probability tables, don't you?
Yeah, it's basically a fix for some of the issues in the underlying Genie.
Yeah.
Yeah.
Genie has been mostly good in supporting actually reading and other stuff, but at least when I originally generated this one, I could read in a Netica network and it would take the structure, but it lost all the parameters. it didn't want to do all that rotating from columns to rows and stuff like that. Make it painful. Okay, so this is my honours thesis BN again, but we're using submodels here. So this is a lot easier to read than the one that I showed you beforehand, but it's the same BN. I've got we've introduced this new concept here, which is a submodel here. So hydraulic habitat there, and I can double click into there, and I get my hydraulic habitat BN here. There's some notation here. You can see these little arrow thingies on the side here. That's saying that there's some parent in another submodel coming into here. And we've got these arrows going out, which is saying that there's children in other submodels. So when I hover over it, it tells me what those networks are. I can look at the different submodels together as well. And I can actually connect links between, well, them like that. Although I just tried to put an arc which is already in there. So so we kind of get this type of thing. It's it's definitely nice to visualize, and when you show experts, I find a little bit kind of like when I'm hacking and building Bayesian networks, I find it a little bit not lacking that flexibility and dynamic aspect to actually build the BN on the fly. Because generally what I do is I'll start building a BN and then I'll chuck away most of it and rebuild it up, and then this kind of makes it a bit of an overhead for that, and it's a bit.
Yeah. It's not a very advanced form of grouping.
Yeah.
So it's, yeah.
But once you've got a BN there, and if you're getting, you're showing it, demonstrating it to stakeholders, or you've got users that are going to go and use the BN within the tool like this is definitely a better way to do it than Netica. So that's Genie. Now the disadvantage of this is that I can make a copy of, I can actually make a copy of those submodels there, but once I make a copy of it, they're forever different networks. So I make a change in one network, the other one won't actually be the same anymore. So it's like me copying my Word document into different files there, which is okay, but often when we want to do these BNs, it's not what we actually want. We want to say that this submodel is the same submodel. And I don't know, I think that's debatable. It's not easy to view the whole full submodel. Huygens does do this flatten out type thing, but I don't know if that's really easy to view this full submodel either. So this is kind of motivations for why we might go into Genie anyway. And also, into Huygens. And also Huygens is well, at least attempting to implement this formal specification called object-oriented Bayesian networks. And I've got a few programmers in the room, so you guys know what object-oriented is, yeah? So you're going to be familiar with the concepts of this, and you're going to see what the motivation is behind this. Who doesn't know what object-oriented programming is? Awesome. Usually my eco-scientists that we're doing this course will have absolutely no idea what I'm talking about. All right, we're probably going to go for this fairly fast then, really. Okay, so object-oriented, we know, proposed in the 90s, all these guys here. We have these, that's some inheritance diagram here, and we have some concept here about a class, of a car class here, which has got methods attached to it and attributes there. Now, OOBN is implemented in Huygens, which is the main tool that I go to for this stuff here. GeniRisk, which is what you guys are going for as well, and I haven't had much experience with yet. Bayesian Lab, which is a really nice but supremely expensive Bayesian network program. They're pitching to the big companies. But yeah, so this is something that you probably will come across with your projects, even if you're not actually implementing it. It doesn't sound, it's when you start really scaling out your BNs, that's when you actually start doing this stuff. Terminology, so this should all be familiar with you. So we have an object-oriented Bayesian network class. It's made up of ordinary nodes and objects, which are instances of other classes. So we can have other classes embedded within our class. An object may encapsulate multiple subnetworks, giving it a composite and hierarchical structure here. So the class has a template for an object, and it's going to have a name. It's going to have an interface which defines what inputs we can go into it and what outputs we can read out, and some hidden part which is like its own business. This is all encapsulation stuff for our object-oriented research. We have some notation here about this. So we have our input nodes, and we denote them by using a dashed node line. They are always root nodes. Yes. They are always root nodes, and they get mapped to a single node in an encapsulating class. Or they can take some prior value as well, so they can be not connected, in which case they just have we just put some prior over our drought condition. And we have our output nodes, which can be any nodes. It can be like a root node, an intermediate node, or a leaf node. And that just will become a parent of something that's in the outer class as well. For example, we've got something here which is rather abstract. We don't know what it means. We have an outer class here, n, which is class notation here. That's got 4 nodes in here, 1 input node x, 1 output node z, and 2 hidden nodes y1 and y2 here, and an embedded class object for class m, which has six nodes in there, some input nodes and some output nodes. Now, some of these nodes here are connected to the input nodes of the input class. So x is connected to u2, y1 is connected to u1, and u3 is not connected to anything, so it's just going to use its prior distribution. And w1 is a parent of this z in the outer class. So we've defined our Bayesian network in this way, and then what happens in Genie, or we can, in Huygen, or what we can actually ask Huygen to do for us is we can flatten it out, and we can see what that Bayesian network will look like.
So
These
what's the connection between x and u2? They're both input nodes, right?
x and, yeah, that's right, yeah.
So how do we know which way it goes?
Well, because, basically just what will happen is the input node will get absorbed up into this node here. These have to be the same nodes. They have to be the same state space. And then this one, if it's got a parent in an outer class outside of that, will get absorbed up into that other outer node there. But so these do have arrows there. I mean, yeah. But they actually become the same node. They get collapsed. So you can see in here that U2 disappears into X. So basically, that's the reason why we don't have an arrow here, is because they're actually just become the same node. And if there was another node outside of that, that would also get collapsed into the same thing. So U2 disappears, U1 disappears, U3 becomes like a fixed node because there's no parent node to it, and we're just using our prior distribution. Our output nodes do stay around as well. So this is one of the things that, So when we have an input node, Y1 and U1 have to have exactly the same state space. And Huygen, if it wanted to be helpful, would give us some refactoring functions and stuff like that. So if I wanted to change the state space here, then it would change the state space in the outer node, but it doesn't do that for us, so it can be a little bit difficult. So again, we got that same problem. Like when I'm building Bayesian networks in that first kind of nutting out the structure and stuff like that, Huygen isn't very good for it. But once we've got a good idea, fixed idea about what we want to build, then we get something that's kind of useful. All got that? You guys all. And you guys should be seeing the advantage of why we're doing this as well. So I think we have these some examples of that. Okay, so we have Mr. Bunce. So Mr. Bunce was a character from Fantastic Mr. Fox. He has his orchard farm, and he's very keen on getting a lot of money out of his orchard farm because he's like a greedy farmer. And he's also in getting people in to model his orchard for him so he can make some decisions about irrigation and spraying his orchard and stuff like that. So we have the small orchards, these fruit trees that can be distressed, and that might be because they're lacking water or they're suffering from a disease and they'll lose their leaves. He can spray to kill the fungus that's causing the disease, or he can decide to irrigate, and he wants to do this to try to maximise his crop output, the crop yield. And so we look at this problem. mostly we're motivated by the fact that there's a very hierarchical structure to it, and it's a complicated system, and we've got lots of different components, and we decide that Huygens the best tool for this process. So the first thing we start off with is a tree. So we have some tree condition here, and that condition can be caused by the fact that it's overly dry or that it's sick, and we can get some indication of what the tree condition is about whether or not it's losing leaves. We have some decisions about what we could do about irrigating if it's dry and spraying if it's sick, and we also know that this drought condition is going to moderate the effectiveness of the irrigation action. So we create our tree model, and we get our tree expert in to help us put the parameters in this BN and stuff like that. And we kind of know that this is going to be coming out of this because this is what we're going to use to sort of determine our tree output. And these are things that are going to be farm level decisions or farm level characteristics. So then we can go up to our orchard. Now his orchard, he's got 3 trees. It's a big orchard. So we're copying each of these trees here. So this is the first thing that we're doing is we've got multiple copies here. Because these are classes and they're instantiations of a classes, if I change the class for any of these trees here, I'm changing the class for all the trees. We know that they're the same thing, which is what we didn't have in Genie. So this is one of the advantages of going to Huygens. We have our crop condition. That's taking the condition for each of the trees out of here and summarising in some crop condition. And then we've got these other things here, which are, again, a higher level to the orchard. So then we go to the farm level here, and this is where we're making our decisions about irrigation and spraying. We've got some model here on what's happening with the drought conditions there. We're putting our utility nodes in here for irrigation and spraying costs, and that's going to be balanced out by some return based on the crop condition there. Yeah. How are we going for time? I can do some more demonstrations. Now, unfortunately, you don't have Huygens on your machines to play around with this. It's because it's just too painful to try to do in our training exercises. But I'll just do some demonstrations on there. So this is our orchard BN pre-prepared, and where's my zoom function? Okay, so we've got these embedded. So this is the farm class, which you can't quite read up there, I'm guessing. And within our farm class, we've got some embedded classes. You can change around the orders of these input nodes here. Orchard's got 3 input nodes and 1 output node: the drought, irrigation and spray, and the crop condition. And the way that I basically connect these is I can just, from the, I can shrink the class, which is what we were seeing beforehand in the slides. I can open it, and when I open it, I can actually connect the output nodes to something else or input nodes into something else. I think Huygens will complain if I, say, try to put a, oh, okay, they have the same state space, so that doesn't matter. But if the irrigation, those 2 irrigation nodes have to be the same node. They have to have the same state space. Huygens doesn't check to make sure that the names are the same or they match up or anything. That doesn't really matter, but it does actually require for the states to be the same names, I think.
Yeah, I think so. At least
the same number, yeah. And then what I can do is when I right-click on here, well, there's a few different ways I can navigate to the orchard class. I can go to my windows and go to orchard up here, my orchard class there, or I can, like what I do in Genie, I can right-click on here and go to show, or rotate into show class there, and that will also jump me to the class here. And then I can do my show class here for the tree BN there. And because I got my tree class, I can go in here and I can change my, we have a new sort of way when we do our table here, we actually open it up like this. and we're doing the rows. No, this is columns. Yep, so Hugen has the columns as well.
Yeah, I think
Everybody has columns apart from Netica actually. Netica is the only one who does the table rows. So we have the columns here with the probability distribution numbers there, which you won't be able to read at all, but you can trust me that they're there. And the other thing is when I compile, we kind of go, it changes into this different type of mode. Whereas in Netica I can compile it and I can do my edits and stuff. Hugen moves us very much into the compiled mode, and then we're running the BN. And because what it's done is it's created that flattened BN there, it forgets about what all the class interfaces and stuff like that. So we need to shift out of run mode to edit mode if we want to make any modifications to the BN. So there's a few little things that you need to get your head around with that. Another fun one that I like is I like the stud farm. So this is a relationship tree between a whole lot of mares and studs, and I will. So we've got Anne, and Anne is the mare of Fred and Dorothy and Gwen, and Dorothy's father is Brian, and we have this whole relationship tree between all these different horses. Within the horse model here, we're looking at, this is a genetic model on how the relationship between the sire, the father, and the mare, the mother, is related to the offspring. And in here we've got 3 different states, basically this Mendelian genetics. So we have the lowercase a, uppercase A, and 2 uppercase A's there. So we might be tracking through some genetic disease or eye color or whatever through these horses. And what I can do is when I go to my compile mode, I can say, it's not very good. Can you actually see okay? It's not ideal. So I can look at, say, somebody down the bottom here, John, and I can see that when I change Anne, his great-grandmother's genetic disposition, we get some idea of what the distribution of these of John's genes are going to be there. Is that too small for you to read, or can you just make it out? Yeah, you can just make it out. Anyway, so that's kind of fun. And then if I want to create a new horse down here, so I want to add myself, I'll put a new horse in here. I can put orchard in here because the class is there. I'm going to call this one Owen. And Owen has John as his sire, and he's got 2 dads, and Henry. He's also his uncle, by the looks of it, is his mare. And so I can then, I've extended my structure of my horse stud farm there as well. So there's a few other little things here. Now, so we have some research students at Monash who are working on these object-oriented Bayesian networks. So there's a couple of things in here which would be really useful, but it's actually really tricky to work out how to implement this in Bayesian networks. So we're all familiar with this idea of inheritance and stuff like that. So if I've got some Bayesian network for a tree, I might want to break it up into 2 different types of trees, timber trees and fruit trees. So Mr. Bunce wants to diversify and get his different types of crops in there and stuff like that. And then his fruit trees might be broken up into pear and apple trees and stuff like that. There's a lot of effort that goes into creating these Bayesian networks, and we want to be able to reuse it in any way that we can. So we're looking at different ways that we can actually sort of implement this within the tools, but none of the tools actually properly implement this yet. And there's a lot of catches in it, so yeah.
That's the weakest part of OO.
That's the weakest part of OO, you reckon? Yeah. Okay. Yeah, I don't know. Yeah, this stuff isn't in there. However, so when I was talking about my Western grasslands model, which I might actually pull up and kill the rest of the time with that actually. I'll come back to that. I'll talk about some of my ways of addressing this stuff. Now the other thing, so we started off talking about dynamic Bayesian networks, and then we started talking about object-oriented Bayesian networks. So if things are clicking in your head, you might actually realise that when I was creating my dynamic Bayesian network and I was specifying a temporal slice, it's like an object. It's like I've created a template there. So we can implement all our dynamic Bayesian networks as object-oriented classes. And that's what's happened here with our fever BN, which is kind of what I showed beforehand about how we had our T1 and our time t and time t plus 1 here, and how they're related to each other. And then I can make copies of each of those instances over time. Now the only difference, when I say that Huygens doesn't really support dynamic Bayesian networks, it just doesn't have a button that automatically rolls it out over time for me. So I have to do this manually, which is really tedious and annoying. And generally what I do is I just end up writing a program with the API to do it for me. But we have basically that representation of the dynamic Bayesian network. And this is pretty much as good as Netica. It doesn't have the kind of nice little bars showing how the belief is changing over time that Genie does have, but it's all pretty much there for that. I'm not going to bother with a demonstration. Now, so with my grassland model, one of the things that I did is I had my transition with a whole lot of different species over time, so different grass and herb species. So each of my species groupies had particular relationships with each other. They were tracking over time, like a seed bank, a coverage, a basal diameter if they were perennial plants, or a number of annual plants if they were a number of plants if they were annual. And so I had a whole lot of different sort of like subclasses of the same one there. Now, none of the tools really supported me actually addressing how they were related to each other, but I kept it in my head about how these all things were. So even though I wasn't using the tool to implement that inheritance concepts, I was actually doing it myself. And that was useful to do that. Another thing that happened with that is my Bayesian network was really, really large. The tools wouldn't compile it to do the exact inference, so I had to go to do a stochastic simulation over time as well. So basically we're just running our Monte Carlo simulation over time. And things go a lot slower. I was thinking I could try to demonstrate, but I'm actually not certain if I want to. So anyway, do we want to have some discussion now before the tea break, or we can just have an early tea break?
I don't want to interrupt the tea break.
Oh, no, I'm ahead of time. I always go a bit too fast through that section.
Just with the objects, as long as the interface matches, like all those various different types of graphs that you'd want to be able to instance.
Yeah.
As long as, I guess you can just define a more flexible way, instead of forcing it to fit into a hierarchy, it's just make sure that those objects all have the same interface.
That's right, yeah. So I had, for my grass model, the way that I did it was I had like my seed bank. So each of my grass herb transition had a seed bank, seeds transitioning over time, and a cover over time. And then it's just, depending on what the dynamics of that particular model were, the seed bank would change depending on what they are. So these particular plants here would have like a higher seed production rate over time, and their seed bank would follow, the changing over time would follow a different dynamic. And the cover would change in different types of ways as well. So if it was like perennial, it would keep on increasing until it maxed out at some level. If it was an annual, then it would all die out in a particular season of the year. And so those types of things. So I'd specify this is my kind of interface, and then I'd just like the actual relationship between each of these ones would change depending on what the species grouping that I was particularly modelling was.
And you'd like if each instance was labelled with this thing is that, and so you had to sort of remember that.
That's right, yeah. Now the thing that would have really helped is when I made some changing about the discretization of these, because these are continuous variables, when I made the changes about discretization about that, I had to go and change everything. and because we didn't have any refactoring type stuff that was supported in Huygen. So I suppose refactoring in the inheritance sense would be really useful to know that these nodes are actually meant to be the same thing. So if I change the states of this one, then this goes to change the states of that one as well. But alas. Anyway, you end up writing your hacking programs to do all this type of stuff. Anyway.